Hello everyone. Today we will talk about Hermite interpolation. It's not convenient interpolation in terms of numerical methods and engineering because mostly we don't contain that much information about our data. However, it's an interesting method to interpolate our function. And let's consider it in more details. The problem with Lagrange interpolation is that when you have more than 10 points, your polynomial becomes very strange. Because assume you have, for example, 20 points, and because your Lagrange interpolation want to pass through every of them, it will behave super strange. It can decrease, increase. Here will be some stranges. So it will be very strange in terms of the picture, and the oscillations will be very large. And to make these oscillations less, we can use either a piecewise Lagrange interpolation, which we will discuss later. But today I want to tell you about Hermite interpolation, which will also stiffen our interpolant polynomial. And the idea of Hermite interpolation is that in our data now, we have not only our values, but we also have the derivative of our function. And here we use the first derivative, but you can also use some other derivatives if you know them. And the idea is the same. We want to interpolate our function f as a sum of, let phi of x, phi. It's a basis, phi I. Then I want to interpolate my function f as a sum of our basis functions times my value, f of I. Here I goes from 0 to n, and plus derivative of my basis functions. Let's, for simplicity, use notation that phi I is f of xi, and fi prime is f of f prime at point xi. And here we use also prime, and our I goes from 0 to n. And as previously, we want from our function so that f of xj is equal to fj, and we can enforce the condition on our basis function phi as following. We want f of phi I from point xj, it will be the delta Kronecker delta ij, which is equal to 0 if I is equal to j, which is equal to 1 if I is equal to j, and which is equal to 0 if I is not equal to j. Then we say that let's here use different function, not the same. So we will have like two bases, one for our function and the another for our derivative of our function. And then here we will use condition that our first basis phi supposed to be 0. And then for the second basis with the hat, we use the condition that phi I hat at xj is equal to 0, and phi I prime hat at xj is delta Kronecker. And as a homework, you can check that the function which satisfies these conditions are the following. Phi I of x is 1 minus 2 times Lagrange polynomial, which we discussed earlier, j prime of x. Here is j, so that keeps the notation the same. Xj times x minus xj and times square of the Lagrange polynomial at point x. And for second basis with a head, we use the following function, which is x minus xj times the square of a Lagrange polynomial. So that's all for Hermite interpolation. It's similar to Lagrange interpolation, but here we used not only the values of our function, but also the derivative of our function. And the problem with that method is that we need to know the derivatives. And usually in engineering, we don't have that information. So Hermite interpolation is a nice technique, but not very useful. Thank you very much. See you in the next video.